All right. My name is Xander Swinney, and for my project, I decided to design a 6 degree of freedom robotic arm. This picture here is the robotic arm that I based my project off of. So, as an introduction, the goal was to design and prototype a 6 degree of freedom robotic arm. I wanted to use inverse kinematics to translate desired end effector position and orientation into joint angle. So to do that, I wanted to use a method called kinematic decoupling. This is a technique used to solve kinematics by separating the position and orientation calculations. The way this works is starting from the uh, desired point and then the desired orientation, backtrack that to calculate the wrist center. From this wrist center, you can then calculate and solve the um, position of the robotic arm. That gets you theta 1, 2, and 3. And then using that same point, you can also calculate the theta 4, 5, and 6. And that separates these two into it separates the inverse kinematics problem into easier problems. For my project, I started by assigning frames to everything. I ran into a lot of issues. I had to do a few iterations. Eventually, I found out that if I put this subframe, which I named frame 1.5, when I put this subframe in here, it effectively translated between 1 and 2. Um, and it allowed me to accurately represent my robotic. So after doing that, I was able to come up with this DH table I used for inverse kinematics. To power my device, I used an old computer power supply. I had it laying around. I took the 5-volt pins from there and I used that to power the Raspberry Pi. Then I took the 12-volt line and I connected that to multiple buck converters. Those buck converters, they step down the voltage down to the motor's specified operating voltage. Um, yeah, and that I ensured that each motor would get uh, enough current to supply the servo at its stall torque. And then the servo driver is powered directly from the Raspberry Pi, as well as a DC. For the structure, I use a 3D printer. I designed everything in. I printed in PETG plastic. For the base, it was printed in 5 different parts. I used dowels, some adhesive, and then I embedded nuts into these parts, and then bolted them together. And the combination of those three things connected this base together. I then went and designed the actual links. The links, I went pretty bare bones on those. I pretty much just printed what I could to connect one servo to the next. So I began coding by creating an I2C driver. Um, so the I2C is a communication protocol that communicates through these two lines, typically in a master-slave configuration. For my device, the master would be the Raspberry Pi, and I only have one slave device, and that is the servo driver. I created an I2C driver that handles all the communication on the I2C bus. This allowed me to do things like I2C.read or I2C.write. and that allowed me to read and write to a specific address. The PCA 9685 is a 16 channel 12-bit PWM driver. This allows individual control of the duty cycle on each one of these channels. I created a driver class that communicates with my I2C class. And that effectively allowed me to run commands like set pulse width on a specific channel and a specific pulse width, as well as the duty cycle. So next I created a servo library. This library used my PCA 9685 class to control the angle of the servo motors. What this does is it takes that desired angle and it calculates the required PWM signal to achieve that angle. Then it sends that signal to the PCA 9685. Next, to achieve the velocity control of each servo, what I did is I created a thread. Each servo can create a thread, and that thread is responsible for getting the servo from point A to point B. And the way it does that is it takes steps towards its target over time. So it will take a step towards the target, and then it will go to sleep. And then it wakes up and it does it again. And on average, it will reach that target with a specified angular velocity. So I can control that, I can set the speed, and I can move to a position at that angle. Now, of course, on my project, I have 6 different motors. So all 6 of those are going to have threads running that are attempting to communicate with the I2C bus. To prevent those from colliding, I needed to use a mutex. So a mutex prevents multiple threads from accessing a shared resource. In terms of my project, the mutex prevents my servo motor threads from accessing the I2C bus at the same time. Basically, one servo motor goes in, triggers this mutex, which prevents any other threads from crossing it. It will carry out what it needs to on the I2C bus, and when it leaves, the next one can get in line. So another issue I ran into was my servos were inaccurate. Based on the given specifications, it was not giving me the angle that the specifications said it would. So I created this servo calibration device. Basically, it hooks up a servo motor to it. It connects to this axle here, and then uses the AS5600 magnetic encoder to record the actual absolute angle of the servo. So what that did is I basically tested the limits. I moved the PWM signal down, and I checked and ensured that it kept moving. Once it stopped moving, that was now my minimum. And same thing for the maximum, and I recorded the angle as we moved along. And that allowed me to get a lot more accurate specifications for my servos. So finally, I created a robotic arm builder class. This class pulled together all of my code, and it sets up controls for the robot. The inverse kinematics for this is still a work in progress. I have code down for this, but it doesn't. The joint angles are not correct. So as of right now, I can set the angle of a specific motor. If I try and set the orientation or the end position, like in 3D space, it gives me an output, but it is not. In the future, of course, the first step um, I gotta fix the inverse kinematics. I need to go over and I need to achieve control over the um, another important next step is safety mechanism. Right now, there's nothing preventing it from colliding with itself. If the arm wants to go through the base, it will attempt to go through the base. There's no code preventing that. Um, and then finally, I want to be able to attach different end effectors to the end of my joint and or to the end of link 6. And I want to wire up an I squared C bus up to the end effector. That way I can control the end effector through. And that's my project. Thank you.